All right, so magnetism we understand quite well, as I was mentioning. Um, it's caused by current. That is when charge moves, right? Remember, everything is made of atoms. All the material that we find, things that you can touch, they're made of atoms, and atoms have, electrons and protons, which are charged particles. Now, usually there's just as many electrons as there are protons, so there's no net charge. But that's not always the case. If there is some net charge, um, and that charge is moving, that's called a current. And if there's a current, there is a magnetic field. That they're related. That they're absolutely related to each other. Once you have a current, you always have a magnetic field. All right. So somehow there are these currents inside of the Earth, which we think we know what they are. It has to do with the outer core of the Earth, the liquid core rotating around, which it's made of iron, um, molten iron, and that of course has charged particles, charges that are moving around. Metals um, get can be charged very very easily. That's why they make really good conductors, like copper, for example. We use copper all the time for to, to have electricity travel from one place to another. All right, so and so when you represent these magnetic field lines, the more of them there are, the stronger the magnetic field. Now, the Earth's magnetic field is it's like I said, it's not, as I mentioned before, it's not the strongest magnetic field in the solar system. In fact, the sun has a magnetic field far stronger. Jupiter has a magnetic field that's about 1,000 times stronger than the Earth's magnetic field. And some of the other planets, it's like Saturn, it's a little bit less than that. Um, but they all have, not all of them, but many of them have magnetic fields. And so the big part of this chapter 6, is when we understand the Earth, or the better that we understand the Earth, the better we can apply that knowledge and that understanding to the other planets, right? That's really what the goal is. I mean, we live on the Earth. We've been studying the Earth for a long, long time, and so we can. It helps us understand what's going on with other planets. All right, so um, and not only in our solar system, in other solar systems as well. All right, so one of the things that you might notice right away is there's actually a difference between the magnetic North Pole and the physical North Pole, right? They're actually offset a little bit, uh, and the Earth's magnetic field drifts. It's not always pointed in the same direction. In fact, we've found that over geological time. So when you talk about geological time, you're talking about hundreds of thousands of years to millions and even billions of years. The Earth's magnetic field flips. So right now. By the way, I know this might seem a little strange, but the north, like the magnetic field that's right here in the North Pole, in what's the geological North Pole, is technically the South Magnetic Pole, and the North Magnetic Pole is down here, right? It might seem strange, but for a compass to work, right? Like, you think about it, a compass is just a magnetic field. It's just a local little magnet that you have that can swivel, and when you look at a magnet, when you look at a compass, the north end of the compass points, towards the north. Well, that like magnetic fields, the north, two norths will repel each other, and two souths will repel each other. It's only a north and a south that will attract each other, so that when the north pole of a compass points to the north, it's actually pointing towards the south magnetic pole. Or anyhow, um, that's just a little point of interest. But what so what I'm saying is, over geological time, and we found this in there's volcanic record that the magnetic field of the Earth has been oriented in different locations. In fact, it has flipped, so that this magnetic South Pole has ended up in the actual South Pole over, I think it's every roughly 200,000 years, and it's not like 200,000 years go by and there's an automatic switch between the North and South Pole. It's just, on average, it switches once every 200,000 years or so, right? It's not like on a clock or something like that. And that actually we don't understand very well, like why that happens. It obviously has to do with current inside of the Earth and the direction that the current is traveling. But we still have to figure out exactly why that's going on. All right, so this is just showing you, a magnetic field. This is a very famous physics experiment. Is you put a bar magnet right down, and then you shake some iron filings, element 26 filings, which there's certain metals that are very susceptible to magnetic fields, iron being one of them. And in fact, they're called ferromagnetic material. Ferro is Fe is the chemical symbol for iron, right? Because that's just the Latin name for iron. Anyhow, this is kind of showing you the field lines, right? So, what else? Direction from magnetic. So we normally think of magnetic field lines as if this top one is the north magnetic field, they leave the north and then they terminate on the south magnetic field. All right. Magnetic fields are generated by large currents. All right, so you have moving charge, or like for like a bar magnet or a magnet that's sitting on your, attached to your refrigerator. That's actually the thing that's moving is currents on the atomic scale. So it has to do with like what the electrons are doing in the atoms. All right, we don't have to go into that in any more detail. This is not a chemistry class or a physics class. We're trying to understand, astronomy, and trying to understand the planet Earth and ultimately compare the Earth to the other planets. All right, so the magnetic field of the Earth is generated by currents in the molten core. So that's the outer core of the Earth. Of course, iron and nickel is what exists there. The current is believed to be caused by the rotating motion and convection. So this is also known as a magnetic dynamo. And by the way, you have to have a magnetic dynamo to generate electricity, right? You have to have a magnetic field to get electricity to flow. And we use this all the time to generate electricity. All right, so the Earth's geographic poles and the magnetic poles don't exactly line up, as I mentioned before. We go back to this picture right here. So you see, there's the the geographic North Pole and the geographic South Pole. They don't exactly line up with the magnetic poles. What else? Oh, yeah. Let's see. Both the strength of the poles change slightly. Oh, so they're saying that they said it's about every 250,000 years. I think earlier I said it's every. I mean, it's roughly every 250,000 years, right? It's not like they all of a sudden, 200,000 years has gone by and it's time to switch, right? So this is just the average values that, that the average amount of time that goes by, and then there's a reversal of the poles. All right, so now we get out a little further out into space. So this is this thing called the Van Allen belt. Is well out. So this is well outside of the atmosphere. The atmosphere is really, really close to the Earth, right? You go up, and I don't normally talk about miles, but you go up roughly 100 miles, and you completely have the entire atmosphere of the Earth within that. Just to let you know. All right, so this the Earth's magnetic field actually extends way out into space, and what's interesting about this is a magnetic field. So this is just in general, a magnetic field will interact with a charged particle. All right, so when a charged particle encounters a magnetic field, it will spiral around the magnetic field lines. Right, so what's going on here is there's charged particles actually all the time coming from the sun. Right, that's called the solar the solar wind. It's known as the solar wind. It's not like the wind on the Earth. Right? It's far more rarefied. It's not. The particles are much further apart. In other words, all right. So anyhow, these charged particles, mostly electrons and protons, come flying off the sun. They take a while before they get here to Earth, and then that they will spiral around the magnetic field lines. What's really amazing is they spiral and they will actually crash into the North Pole and the South Pole, right? And that's in fact what we call the auroras, right? That's what is the cause of the auroras. All right, we'll get back into that in just a little bit. Now, some of the charged particles will bounce back and forth in these regions called the Van Allen belts. So these are like these regions right here are shells, right? So imagine like a shell around the Earth of these charged particles. I mean, you're just seeing a part of it here, and so these shells are the charged particles that get trapped and bounce back and forth. But by the way, these are very very strong radioactive belts. And when the astronauts, for example, when the astronauts get far enough out into space, if they do, most of them don't go that as far as the Van Allen belts, but like if you're going to the moon, for example, you have to pass through the Van Allen belts, and the astronauts cannot be outside of their spacecraft because that would be extremely harmful to them. The spacecraft will protect them for the Van Allen belts. By the way, just a quick note: the Van Allen belts, like when the United States first sent up a satellite into space, the very first one, it was called Explorer 1, and that's actually what its mission was. So this is before humans were put into spacecraft. So the Explorer 1 was actually trying to map the Van Allen belts. Van Allen was a guy who predicted that they were there, and in fact, we went out and measured that. We measured the fact that they are actually there. So that was